All right. So, when I go to conference, I never miss the keynote. You know why? Because you can really sense the future direction. Okay. Today, we have a very special keynote. So, before I introduce the keynote speaker, which I'm not going to introduce the keynote speaker because this is the first time out of 62 years we do have a keynote chair. Okay, he also did put huge amount of time and study, to find the perfect right person for our society. Please welcome Nikhil Barlam.
Thank you, Hunjay. It's my great honor to be keynote chair for the first time. The purpose of creating this position was to have a consistent, transparent, long-term process for the finding and selection of keynote speakers. So with that in mind, since we're going to restart that process again for next year, I'm going to take the bold step of giving you my email address. It's nikhil.balram@mojo.vision. Please don't send me spam. If you have ideas for great keynote speakers for next year, please send them to me. We'll start the process like any other sales process. It starts with a broad funnel, and then we'll down select and work our way towards next year's amazing keynotes. But let's now go on and talk about this year's amazing lineup of keynote speakers. It's my great honor to introduce the lead-off keynote speaker, Professor Moungi Bawendi. I'm going to read through a short, summarized version of his bio. I would be here half an hour if I was trying to detail all his accomplishments. Professor Bawendi is one of the initial developers of the field of colloidal quantum dots. He has followed an interdisciplinary research program that probed the science and technology of chemically synthesized nanostructures. The work has advanced both the fundamental studies of nanomaterials as well as their applications. Bawendi's lab at MIT has pioneered the synthesis of high-quality quantum dots and developed novel tools for the applications of nanomaterials for light emission, photo detection, spectral sensing, solar energy harvesting, and bioimaging. He received his AB in 1982 from Harvard University and his PhD in 1988 from the University of Chicago. This was followed by 2 years of postdoc work at Bell Labs, working with Louis Bruce, where he began his studies on nanomaterials. He joined the faculty at MIT in 1990, where he continues to be a professor. He is a fellow of the American Association for the Advancement of Science, a fellow of the American Academy of Arts and Sciences, and a member of the US National Academy of Sciences. And oh, one more thing. He's a co-laureate of the 2023 Nobel Prize in Chemistry. Please join me in welcoming Professor Bawendi.
Okay. Thank you for this opportunity to give a presentation here at SID. I was here once a few years ago. It's really an amazing conference. A conference that looks deep into the future of what displays are going to be like. And you'll hear that from the next few speakers. But I'm going to go backwards. I'm going to go backwards a few decades to tell you about the origin story of quantum dots. Who would have thought 30 or 40 years ago, when these materials were first discovered and created, that they would be so ubiquitous around us? And this Nobel Prize in chemistry for the synthesis and the discovery and synthesis of quantum dots really is a Nobel Prize for your community. Because without the ubiquitous application of quantum dots in displays, I don't know if there would have been a Nobel Prize for quantum dots. Maybe in 10 years. So with that, let me tell you about quantum magic and quantum dots and my journey. What is a quantum dot? Well, many of you already know what a quantum dot is. It's a small particle of semiconductor, not silicon. Silicon is actually quite hard to make as a quantum dot. Usually binary semiconductors like 2,6 like cadmium selenide, 3,5 like indium phosphide. They're usually on the order of a few nanometers, a few hundreds to thousands of atoms, 5 to 10 nanometers. And because of that size range, they have very special properties for the electrons. When you think of an electron in a circuit, like in a computer chip, you think of a particle moving around, doing computation or carrying energy to your tool, like a drill or a toaster oven. But if you take that electron, and you know that if you take that electron and you put it in an atom, it doesn't behave like a small particle moving around at all, like in a hydrogen atom. Well, it's kind of the same thing if you try to stuff it in a nanobox. If you stuff it in a nanobox, there's the Heisenberg uncertainty principle. I know some of you have heard of that. You can't tell where it is and know its velocity at the same time. And in nanobox, that electron is no longer a particle. It behaves like a wave. And that's the quantum property that's at the root of why these materials are so interesting, so fundamentally interesting. And our nanobox are the quantum dots. And this stuffing of the electron is called quantum confinement. We know the properties of wave intrinsically. We know them from sound waves. We know that if you have a flute, the pitch of the flute is going to be deeper than the pitch of a piccolo. And that's because the cavity is bigger for a flute, right? So the same thing happens for that electron wave in a box. The size of the box then is reflected in this case, not the pitch, but the energy of the electron. You see the same thing in organ pipes, right? So in organ pipes, you have many, many more organ pipes sizes than for the flute and the piccolo, and you get a variety of pitches. So you can see then that if you were able to make nanoboxes in a variety of sizes, you would have a symphony orchestra, in terms of the pitches you would be able to make. The big pipes have a deeper sound than the small pipes, and the same thing for the particles. So if we look at a series of particles, in this case here, let's talk about cadmium selenide, since cadmium selenide is essentially the hydrogen atom of quantum dots. And by that I mean it's the most studied material. It's the one that we go to when we have questions about the fundamental physics or chemistry, and we learn new things by using that material. So if we look at a size series, and we want to put an electron in those nanoboxes, how do we do that? There are already a lot of electrons in there because these boxes are full of atoms. The way we do that is by liberating one of the electrons and allowing it to occupy the entire box. And we do that by shining light. We excite an electron, we rip it out of the atom that it originally was next to, and now it's free to occupy the box as a wave, leaving behind what we call a hole. Eventually, that electron goes back to fill that hole where it came from. And the energy of the wave of that electron then gets transferred to light energy, another wave, electromagnetic wave as opposed to electron wave. And light comes out. Light comes out then at different colors. The small electron wave creates a small wavelength of light, or bluish, in the case of cat selenide. And the longer electron wave in the bigger box creates a longer wavelength of light further to the red. And then you see this beautiful fluorescence, which now is the basis of green and red in many displays. So back in December 2023, I had the opportunity to be with Lou Bruce and Alexei Akimov, the other two co-laureates, and received the Nobel Prize for the discovery and synthesis of quantum dots. The Louis and Alexei were the discovery part. That was 40 years ago. They worked in the early 1980s, late 1970s, on understanding this phenomenon that they had discovered. Alexei Akimov was working in the Soviet Union in Leningrad, now St. Petersburg, And he was interested in understanding the color that you could see in stained glasses. It was already known that the red in a stained glass window in an old cathedral is from small particles of gold. Faraday had explained that a long time ago, in the 1700s. But he was interested in the other colors. And, you know, the recipes were complicated. All sorts of things were added to these glasses, but there were a few elements that seemed to be critical. Alexey then, by removing every other element except for the critical ones, and processing the glass at different temperatures, heating it up, cooling it down multiple times, etc., was able to create colors with a few elements, for example, cadmium and sulfide, cadmium and selenite, copper and chloride. And he observed that depending on the processing, different colors would come out. It was all the same element, but different colors in glass at high temperature. He used small-angle X-ray diffraction and correlated the size of the little particles that he was able to measure with the X-ray with the color that he was observing. And because he was surrounded by physicists at the time who were deep into the science of quantum wells are ubiquitous in communication as lasers now today, he was able to understand the effect that he saw as a quantum effect and wrote a paper in the Soviet literature that had the title Quantum Size Effect in the first three words of the paper. Simultaneously, in parallel, across the world, Lou Bruce at Bell Labs in New Jersey was interested in the kinetics of electron transfer from a semiconductor to an electrolyte, to molecules in an electrolyte, for the purpose of creating fuel from the sun. This was a time of an energy crisis, OPEC embargo of the late 1970s, the creation of the National Renewable Energy Laboratories, and under the Carter administration, the issue of energy independence and renewable energy was really key. Then I remember, as a student, seeing lines of cars waiting at gas stations. Really strange sight, you know, in retrospect. There was not enough gas, not enough gasoline. So Lewis, in order to get better signal to noise, realized that he needed to make particles as opposed to a surface of a big bulk semiconductor. So he made his particles smaller and smaller using recipes from the old German literature, from Hanglein's group in Germany, for instance, using cadmium sulfide. And this was all done at room temperature or even lower at using zero Celsius type of chemistry. And observed that if he left his particles to overnight, that the color would change. It would redshift. At first, he thought it was a classical effect called Mie scattering, the same effect that happens, that creates beautiful sunsets, that creates the red light, scatters less than blue light, right? Then realized that these particles were way too small. He had at his disposal the tools at Bell Labs, like a transmission electron microscope. And so he used that to correlate the color that he was seeing with the size of the particle. And he also, surrounded by physicists working deep in quantum wells at Bell Labs in communication, was able to understand that the effect was due to quantum confinement, and also wrote a paper called Quantum Size Effect, the same three words in both papers. They didn't know about each other. It wasn't until a number of years later that Alexey and Lou Bruce met each other, and about 3 years after Lewis wrote his first paper, did he realize that Alexey's paper existed, and sent him a note inviting him to begin to talk about these things, which somehow involved the KGB, because that was very strange for an American scientist to reach out to a Soviet scientist at the time. Alexey is now in the US, as is Sasha Efros, one of his early collaborators, so there was a big vacuuming of Soviet scientists into the US a little later. So where do I come in? I was a postdoc with Lewis in the late 1980s, and it was very clear already with Lewis and his postdocs, his previous postdoc, Paul Vasados, and his collaborators, Mike Steigerwald, that making good samples was really key to understanding the physics. Really what we were trying to understand was this transition from atomic properties to bulk properties. The properties of an atom are completely unlike those of a piece of bulk material. Somewhere in between, the aggregation of atoms to make the bulk material creates the properties that we see at the end. So what happens in the middle? There was a community working on metal clusters at the time that was asking the same question, making clusters one at a time bigger and watching properties evolve. And semiconductors, same thing. You know, how do you, so, but we were going to a bigger size. The transition to the bulk material for semiconductor happens at a size that's much bigger than for metals. So that made it more interesting, for me at least. So I joined Lewis as a postdoc and was given a task to figure out something that, that puzzled them at the time. And it's through that, trying to solve this puzzle that they had given me, that I stumbled across a way to make the particles that eventually I brought to MIT and eventually led to our synthesis. So let me bring you back now 35 years or so to the synthesis that Paul Vasados and Mike Steigerwald and Lewis were doing. So, and I have these transparencies here from the 1990s. When you get a Nobel Prize, you go deep, into your past, and you okay, so what was I doing back then, right? The average gap between the discovery and the Nobel Prize in chemistry is 30 years. So for me, that's exactly on the dot, right? 1983 to 2. For Lewis and Ekimov, it was 40 years. So the way that they were making the quantum dots at the time was by making little bubbles of water, little droplets of water in an oil and detergent mixture, and adding salts, like cadmium salts, and that limited the number of cadmium atoms in the bubble, because they were very small bubbles, and then adding a selenium source here, bis TMS selenide, to react with the cadmium at room temperature in the presence of the water. And then Steigerwald's genius was to say, oh, this is still a growing surface. I can add another source of selenium, but now bound to an organic group to create a particle that's decorated with, in this case, phenyl groups. And that new particle is no longer dispersible in water. It comes out of the little bubble of water and comes out as a powder, which then you can purify and redisperse in other solvents. They had discovered that if you take these particles, which were made at room temperature in the presence of water, which were actually quite defective, misshapen, huge size distribution, lots of defects, and you were to heat them up a little bit in another solvent that we called a Lewis base, that they would get their structure a little bit better. Things would just improve a little bit. And part of my task was to find out if there was other Lewis bases that could do similar things. So I went to Mike Steigerwald and I said, okay, what kind of Lewis bases do you have in your lab? And he said, we've got phosphines and amines and all these things. And I started cooking. And I did what, in retrospect, was a nucleation and growth kind of synthesis. I made really tiny particles at room temperature in water, took those little tiny particles with all the other stuff that came with it, and dispersed them in what is now in tributylphosphine with a little bit of tributylphosphine oxide, and discovered that sometimes these particles would keep growing, and the color would be this beautiful orange color. And for the first time, we could see light coming out of these solutions when we shone UV light on them. So before that, with that synthesis in water, there was no fluorescence. They were dark in the presence of blue light. But now we could start to see. And it was really a moment of aha moment, right? You see something that you didn't expect that's really changes your perception of the material. But it didn't happen all the time. And so from my transparency from 1990, I used a very scientific term to describe things that don't happen all the time and that you don't understand. It's called magic. So in retrospect, part of what was happening is that we brought in a lot of water in there, and there was a lot of oxygen, and the surface of these particles really don't like water, don't like oxygen. Okay, then I moved to MIT and was joined by two incredibly talented students, Christopher Murray and David Norris, was my first two of my first three students, and Manoj Nirmal, who was also waiting in the wings. And I tried to reproduce my Bell Labs things because I had proposed to really do a size series from the smallest to largest and really watch this evolution of properties. And nothing worked. The occasionally became never. And that was very disturbing as a young assistant professor. And so Chris Murray and David Norris and I, it's really largely Chris Murray working late at night trying to get his frustration to fix those frustrations of nothing working. We decided to ditch the water completely. First of all, it was clear that was a bad idea because it would just oxidize the surface. And what I had been doing was enucleation and growth. So let's just do a different kind of nucleation and growth. Let's get rid of the water, get rid of the oxygen, go to completely organometallic chemistry. And that was the birth of the what we call today the hot injection synthesis. We didn't call it that back then. And this little cartoon from 30 years ago is still what we see in talks today. Still, you scale it up, and you make huge quantities of quantum dots. A way to inject the precursors in a hot solution. The injection creates little seeds of semiconductors. That's the seeding part. The concentration goes down. Now you are no longer able to make seeds. Instead, you grow, and you have a slow growth that gives you a uniform size distribution. It's very much like what, the process that happens when it snows. Yeah, you have little seeds of ice that form in the clouds, and on a humid day, when it's not too cold, those little seeds that were generated in the clouds drop through the atmosphere and build up more and more water on them. The snowflakes are all big and fluffy, right? They're all about the same size. So you have the nucleation in the clouds and the growth through the atmosphere. On a cold day where it's very dry, those snowflakes are really small, right? So the growth stage really can allow you to optimize the size and have a nice distribution of sizes. So I have now a laser printer. This is 1993, so we use a combination of handwriting and laser printer. So I describe here then the process that we made, the importance of nucleation and growth, the importance of having these molecules on the surface to give it sort of the idea that you have a big molecule that happens to have an inorganic core, the decomposition of precursors to form the nucleation, and the extraction as a powder followed by purification. In this case, what we call size. And we wrote a paper, and this was my first paper at MIT. And it saved my career. And there's a couple words here I want to point out. It was a simple route, and that turned out to be really important in a single reaction. Because when you want to scale something up, the number of steps is correlated to the cost. So if you can do it in a few steps, it makes things a lot easier and much cheaper. So that turned out to be really important. Consistent crystal structure, monodispersity, and a way to purify to get really narrow distributions. And from that paper, we have particles that are basically all the same, a crystal structure that is the same as the size of the particle. The solid line is the model, and the dotted line is the experiment. It shows you that really what we were doing was essentially like scooping out a little piece of the bulk, which then allowed us to study the physics. And for the first time, we were able to see these extra peaks in the absorption spectrum, which are basically, if you think of sound waves again, the harmonics of your fundamental, right? and this incredibly bright, at the time I thought it was incredibly bright fluorescence, and narrow, looking very saturated, beautiful reds and orange and greens, et cetera. The quantum yield at the time was probably 15 to 20%, and I thought, wow, this is really bright. And I told my colleagues in Germany, one of my colleagues in Germany, Horst Weller, and he said, well, 10% means that 90% of your sample is trash, but he used a much more colorful word to describe 90% of my sample. Well, I think that's energized the field because today, these emission quantum yields are essentially 100%. Chris, for his thesis, redid this whole thing and showed that you could get exquisite size control. So these are all different samples going from about a nanometer in size all the way to about 15 nanometers in size. Exquisite control at the nanoscale. And the Nobel Committee said, these formed the seeds of nanoscience and nanotechnology because those words didn't exist back then in '93. We didn't have the word nanoscience and nanotechnology. It was just the beginning. And that showed that we could control material at that size scale and really change its properties with new properties. This is what it looked like. This is now from 2010, a YouTube video. And let's see if it's going to work. OK, so this is the injection, which is still kind of the way we do it today, and the way it can be scaled up, of the precursors, the fast injection, and then the color change, which is the little seeds, like the seeding the clouds, right? Sudden seeding, and now we have a slow growth period which we can monitor in situ if we want to. And I'll spare you the 20 minutes of growth here as he's taking samples out. And we'll see that the sudden change here is because we've got a gap of 20 minutes, and now we have these bigger particles, and he's still taking samples out as we watch. And then you can see now, if you dilute them out in solvent, you can see the change in color as a function of time. So with in situ monitoring, you can really get really exquisite control of the output. Then if you put a UV light on it, you can see the light, the fluorescence coming out. OK, so then when you have that, then all the same size, you can realize that they actually these particles want to create solids themselves. These are like artificial atoms that can then organize into artificial solids that could potentially have new properties. This is an active field of study today. How can we get different kinds of quantum dots and different kinds of nanomaterials to talk to each other in a solid? And these solids could be fairly large. This is in a light microscope here on the right side here. This is the work of Sherry Kagan in the early 90s as well, working with Chris Murray. Another big breakthrough was in the mid-90s when, following work that Mike Steigerwald and Lou Bruce had actually thought about in the 1980s, which I worked on as a summer student at Bell Labs, that you could actually grow a shell of a different kind of material on the initial core to protect it from the environment. And that core shell growth, or core multiple shell, which allows you then to engineer the wave of the electron inside the particle exquisitely, is what allowed us eventually to get to these 100% quantum yield materials. And a series of papers from Chicago with Margaret Hines, Philippe Guillaume, from my group a little early on, Bell Labs, Paul Rosados, all basically converged in the same idea. And when you see then the properties of this, you see the narrow emission, but you see an absorption that works in the blue. And all these colors can be created with the same blue light. And when you combine that with a gallium nitride diode, which was basically being invented right then, the late 90s, you have a new way of creating color. And this is a new way that is used in displays. So let me speed up here. By changing the organic solvents, it was clear that you could change the shape of the particles, new morphologies. You could bring them together. This is a combination of semiconductor and magnetic particles that are magnetic and fluorescent at the same time that can be used, let's say, in biology by combining imaging, fluorescence imaging with MRI. And these are beautiful little structures. They're superstructures of particles, all the same size, now 100 and so nanometers, with the magnetic particles in the center and the fluorescence one on the outside. The first application, remarkably, was in biology. That's because we were chemists, not display engineers. And so in biology, this turned out to be a really hard application because you have to have these particles that really don't like water. You've got to protect them to be in the biological environment. First company, Quantum Dot Corporation in 1998, now part of Thermo Fisher, commercialized this. We eventually went deeper into this shortwave infrared, and so this is an image of a mouse with a tumor there with the creating these composite particles, and you can see the flow of these composite particles microscopically in the healthy tissue going really fast. This is using night vision now because night vision penetrates much deeper in tissue than visible light. And in the tumor here, you see these little dots not going anywhere, showing you why it's so hard to deliver therapeutics to tumors. It's not that they don't work, it's that you can't deliver them. Of course, the big application came in downshifting color, just like for biology, but now actually easier than biology because we could stay in polymers, we could stay out of water. The first commercial product that I show you here is actually warming the light of an early LED lights. And this was fine when LED lights were $100 a piece and you could slap on a filter that cost a couple bucks and make some money. But if you want to do that today, you've got to take the dots and put them right on the diode, and that's a lot harder because there's a high flux and there's a high temperature. That's still a subject of engineering and science today. The first display was from Sony, the same idea, using blue LEDs as a source of light and then downshifting to the red and the green. Using cadmium selenide particles, Samsung quickly realized that it would be perhaps a better idea to have indium phosphide in there, get rid of the cadmium, and created the QLED brand. And today, we have OLED TVs where the OLED is blue and the dots are inkjet printed to downshift the blue into the red and the green. Really an incredible technology, really bright, beautiful displays. Luminescent light concentrators used to harness solar energy, where you have the light coming in, the downshifting to the red and capturing the red light at the edges with little tiny solar cells, for instance. Downshifting from the UV to the infrared to help infrared sensors see in the UV. Very easy. You just slap on a little film of, in this case, lead sulfide particles that emit at 1.3 micron. They absorb the UV. And my students had fun here creating a little video of a mock-up scene of two spies maybe in Warsaw or something, during the Cold War. One of them has they're exchanging suitcases. One of the suitcases has a UV tag on it. And this night vision sensor is half-coated with lead sulfide to downshift. And as they exchange suitcases, you can keep track of the one that's tagged because you have the lead sulfide. So on this side, it's coated, and then you get to the part that's uncoated, and the night vision camera is blind to it. So a little bit of lead quantum dots on top of the sensor then allows you to expand the range of the sensor all the way from the UV and then into the infrared. Light in, light out. You can have current in, light out, and that's the electroluminescence, which is the next frontier of displays with quantum dots. It's hard, but every year there's more and more progress, and it really is around the corner. Light in, current out, that's photovoltaics, or also light sensors, in this case in the infrared, in the SWIR region. And there are companies, for instance, SWIR Vision Systems, that are developing these products. So what did we do? We created the field, created chemically synthesized and engineered functional nanoparticles, starting with semiconductors, but the same ideas of this exquisite control of size applies to metals, semi-metals, magnetic materials, ferroelectrics, you name it. The property changes as you get to small size, and if you can make the particles all the same size, you can create this new periodic table to assemble different kinds of properties together to try to create new solids, new assemblies. The applications, the big one, of course, is the displays. Lighting is still one that's going forward. Biomedical imaging is still going forward. You can buy quantum dots from Thermo Fisher and many other companies. Light sensing, solar energy. Catalysis and photocatalysis are ones that I think are in the future. Quantum systems is something that I'm working on right now as light sources, quantum light sources. Funding came from all over the place. At the beginning, largely from government, but as application progressed, more and more with companies, from Samsung, from DuPont, from HP, from the energy sector, from ENI, and for solar, for instance. And in my group, it took a lot of students to get to where we are. These are the heroes, really, the students that did all the work. About 150 people over my 30 years. Then you multiply that, but all the groups that have been working on quantum dots, and it's a huge, huge family worldwide today. And I thank you for your attention.